my curious friends. In this video I'm going to talk about impulse, momentum, and conservation of momentum. In this video we'll be mainly talking about ideas, some problems, and then I'll have another one where we mainly solve problems about conservation of momentum. Idea is to understand what is impulse, what is momentum, solve simple problems involving them, and then understand conservation of momentum and solve problems involving them. Ideas are related to hitting something and giving them an impulse, like you see in this figure here, picture. The golf, when you play golf, you hit the ball, you give it an impulse. That impulse changes its momentum, so we'll talk about that. Similar idea here, if you hit a soccer ball with your head or feet, give it an impulse, you apply a force for a certain amount of time, and that causes a momentum change. That's the first part of the ideas here. Second part is in a system, when there's no outside force applies, momentum is conserved. And that causes different types of motions. For example, in this picture here, we have an octopus pushing jet of water in one direction, and he's moving in the opposite direction because of conservation of momentum. Initially he had zero momentum. Finally he should also have zero momentum, so if he pushes the water out, he should move in the opposite direction, and these should cancel each other. That's how actual rockets also works. So the first idea here is an impulse. When you again hit a soccer ball, there's actually a certain amount of time you apply your force. So you apply a force, the object deforms a little bit. From here to here you have a certain time, short amount, but there's a certain time we apply that force. And that's these two things decides what is the effect or impulse we have on that object. And the impulse is calculated using applied force, average force applied times the time it takes for it to apply. So this guy is here called impulse. How much impact you're given to an object with your force. This is force, this is time. So force has unit Newton, time has unit second, SI units. So the unit for impulse is Newton times second. A better way of expressing this is kilogram meters per second. But you can also leave it as newtons times second. If we have a force versus time graph, we can use the area under that time to find impulse. That's another idea here. So a simple question could be, I have a force I apply to an object. The figure shows smoothed force versus time graph. On average, that's how we apply the force. And the time we applied is about 8 milliseconds. That's a logical time. I'm going to convert this to second, millisecond to second. Milli to a regular value, like millimeters to meters, the same. So 8 milliseconds will be 8 times 10 to minus 3 seconds. Or divide 8 by 1,000. So 0.008 second. So 1 millisecond is equal to 10 to minus 3 seconds, or the same thing, 1 second is equal to 1,000 millisecond. Here both takes me to there. Force is in Newton, no unit conversion is needed. Then the question is asking me, what is the impulse on the ball? Notice here I'm going through the first steps. As I read the question, I draw an ugly picture, which is already drawn for me here. Look at the given values, which are already given. All I needed to do a conversion here. And then I go back to question. And so I already did some thinking. And then go back to question and see what I'm asked to do. What is the impulse on the ball? So assume you're applying this force to a rubber ball. What is the impulse? Simply the area under. Area of a triangle is found the base, which would be the time here. Let me draw a straight line here. Base, which will be the time here, times height, which will be the force here, divided by 2. This just a simple review here. So my base is 8 times 10 to minus 3 seconds. My height is 300 Newton divided by 2. That's the area. And it will be 1.2 Newton times second here. Again, I can write this guy as kilograms times meters per second, also expressed in that format. Then B tells me what is the average force on the ball. The average force can be found using this equation here. Notice that the force is changing overall. We can find what it is on average by using the impulse is equal to average force times delta T. In book it's F average is used, F average. But I'm gonna go with F here. Know that this is the average force in the impulse equation. And simple algebra, then I can solve for force dividing each side by delta T, and it will be about 150 Newton. Impulse and momentum are related. If we can all logically know that if we apply an impulse to an object, for example, I'm hitting a hockey puck, I will change its speed, right? And that the amount of time I apply this force will make a difference on that. So when I apply a force for a certain amount of time, which will cause an impulse, and I can find it using F delta T, it will change the speed of the object. And here we will look at m delta v, mass times the change in speed. It will be equal to mass times the change in speed. Why is mass important here? Is that if I apply my force to different masses, the change of speed will differ, right? If I'm applying a force to a hockey puck, for some certain amount of time, I'm going to change the speed. If I apply the same force to the same amount of time to a bowling ball, for example, the change in speed will not be the same. So mass also matters here. And this mass times velocity is actually called momentum. So again, if I apply a force, I'm going to change velocity, but the change in velocity will matter with respect to mass. How large is the mass I'm applying a force? So we need to define a new quantity here, which will be momentum. Assume you drop in a same size of ball on your computer, and one is a rubber ball, or one is a sponge ball, the other one is a metal ball, right? You're dropping from the same height, they will drop with the same speed, but the metal ball, so you have a rubber ball and you drop in a metal ball, same size, from the same height, they will fall on your computer with the same speed, let's say. But you guys know that the metal ball will make more damage, significantly more damage, because we have larger mass. Thus, same speed, larger momentum. So momentum is important. How mass changes things are important. So we have the definition of momentum here. Momentum is a vector. Which direction object is moving before it hits something or so on is also important. This is a very important fact here. So we have these arrows there showing that. And it's going to be in the same direction of velocity. And change in momentum, we can always find m times change in velocity. Momentum being vector, it could be along x, along y, or it could be along any random direction. If that's the case, we can find its components regularly, how we were finding the vector components. For example, if this angle is theta, remember we always look at the angle with respect to horizontal axis, which should be x, as we call it, x. And the x component will be momentum times cosine theta, y component will be momentum times sine theta. We can also, if we know the velocity, we can take the velocity components to find the components of momentum, which will give us the same result. So x momentum m times vx, or find the momentum times cosine theta, same thing, and y momentum is m times vy, and so on. So the summary here is, when we apply a force, we apply an impulse, and that impulse causes a change in momentum. And we can always find a change in momentum, the final momentum minus the initial momentum, or delta p is another way of showing it. Remember, delta is always changes in our context. And we have to be careful about the fact that momentum is a vector. For example, here a putter delivers an impulse to a golf ball, applies an impulse to it. Initially zero momentum gives a momentum. An applied impulse as a vector equals to change in momentum. Here, change in momentum is the same as the final momentum because initial momentum was zero. Here, you are a soccer player, you hit a ball comes towards you with P initial, you hit it, apply a impulse, change its final momentum, you will look at delta p. This equation is also given in the book, you can use it if you like, but I'll go with this always. J as a vector is equal to delta p. It will always be p final minus p initial as vectors. Here they use a different approach for the difference, but I'm going to go with the approach, vector subtraction approach we discussed on the beginning of the course. So if I'm taking the difference of vectors, I take the first one as the same. So I'm going to carry this p final here as is. Let me use a straight line. I'll do my best to carry it as is, but you guys will get the idea, hopefully. And p initial, that's my p final. And then what we do is we inverse the second vector. So I'm going to inverse that p initial. It would be the same size, but opposite direction and same orientation. So that guy would be my minus p final, right? Minus p initial. So I'm going to take that minus p initial and add it to p final. This guy is p final here. Sorry, folks. So now I'm going to add p initial, minus p initial to this, which will be something like that. And from the beginning of the first vector to the end is always the final vector. This will be my J. Notice we got the same result. Again, they use a different approach here. If you already know that, you guys go ahead and use it, but I didn't talk about it, so I'm not going to use it. So as you take, the bottom line is, as you take the difference, p final, p initial, note that they are vectors. You have to go with the vector difference. Here is a quick question, a 2 kilogram object. So we have an object with 2 kilogram. Let's say it's a ball. And its mass is 2 kilogram. Moving to the right with a speed of 0.5 meters per second. This is its initial speed, 0.5 meters per second. Experience the force shown. So we have a force graph here. What are the object's speed and direction after the force ends? The positivity of this graph shows that the force is applied to the right. So before picture, we're going to go with before after pictures here. So let's get used to it. Before, the guy was going with this speed, and then for a certain amount of time, we apply a force to it. What will happen when we apply a force? And as you see from the figure, force is constant, 2 Newton, right? I read it from the graph. So I apply a 2 Newton force to it for a certain amount of time, delta t. So this force will cause an impulse. There will be an impulse, in this direction, right? And this guy will have a different final speed. Apparently, obviously it will increase. We're pushing it in the same direction. This will be the after picture. Again, how do I know I'm pushing it the same direction? Positive direction. Generally, we take as positive x to the right, and the object is moving to the right as well. Now I know this equation, J is equal to delta P. There's an easy approach here, and I'm going to show it to you folks. Delta P can be expressed as m delta V, and that will be mass times the V final minus V initial. And knowing V initial, we can find V final. We can directly go with this algebraic equation. And the result will give us, if V final is positive is to the right, negative is to the left, that will tell us what the direction is in this simple case here. Now, how do I find that J is, as we discussed before, is the area under. So this area is equal to J, which is equal to delta P, or m delta V, m times V final minus V initial. Knowing V initial and m, I can solve for V final. What is that area? It's a simple rectangle, so the area is equal to this value here, 2, and put in units as well here. We are doing physics here, right? We have units times 1 over 2. So 2 Newton times 1 over 2 seconds. 1 Newton times seconds. 1 kilogram meters per second. Here's why I was insistent on Newton times second is the same as kilogram meters per second, because we're going to solve for speed here, and it's nicely will give us the units. So I have here 1 kilogram meters per second. I'm going to carry this here, actually, this whole thing, and this will be equal to that, guys. So let me carry all that here. We run out of space there. Then I have this 1 kilogram meters per second is equal to m times V final minus V initial. I know V initial, I know m, I'm going to solve for V final. So first of all, I'm going to divide each side by the mass, right? This guy will cancel, and I'm going to input here 2 kilogram. 1 kilogram meters per second divided by 2 kilograms is equal to V final, I don't know, minus V initial, 0.5 meters per second. Notice here how kilogram cancels nicely, and I have meters per second, and the unit of velocity is meters per second, so everything works out nicely if I use this unit. If I stick with newtons times seconds, it could have confused me. Yeah, that's all. So what do we have here? 1 over 2 is 0.5 meters per second equals V final minus 0.5. That's minus unit times. Oh, let me do that better. V final minus 0.5 slowly meters per second. And taking this guy to the other side, minus goes as plus. Bottom line is my V final will be 1 meters per second is positive, is to the right. I already logically decided it should be to the right, and that's the answer there. Bottom line, summary of this part is impulse is equal to change in momentum. Impulse can be also found using area under the force versus time graph. Alright, here is all the solution given. I already solved it in the previous page, and answer is given. Another quick question. A force pushes on a cart. It will apply an impulse and make a change in momentum, right? So let's say it's applied delta t, it says 1 second. Let's put that in here. So a force pushes a cart in 1 second starting from rest. We initially 0. To achieve this, starting from rest. So what will it do? Let's call this before. And a bit later, this force will cause a momentum, change in momentum, right? Initial speed was 0, it will have a final speed. Because we have J which is F delta T, and that's equal to delta P, or M delta V. These are all the same things equal to each other. If you have an equality like this holds, that holds, and that holds all together separately. You can use them. So what's going to happen shortly? Before, after? Simply, I'm going to say F delta T is equal to M delta V. That's the most useful one here if I'm looking for velocities. So what will happen? Depending on how large if my impulse is, right? That's impulse. I'm going to have a larger final speed. Speed change. I have a larger speed change and larger final speed. And delta V is V final minus V initial, right? And V initial is 0 here. Now, to achieve the same speed with a force half as big, so if I apply half as big force, right, F over 2, I should apply twice larger time to achieve the same impulse, which will give me the same change in speed. So if I'm applying half the force, I should apply twice larger times to get to the same speed. What should be the time, or how long I should push the cart? I should push it for 2 seconds if delta T was 1 second. You can really work out the math as well, but it's a simple idea to see impulse causes the change in momentum, change in speed. If I want to apply the same impulse with half force, impulse is defined as force times the time, I should apply it twice as long. Impulse momentum can be used, well, not can be used, it's applied in our daily lives. For example, hedgehogs quite often falls, and as they fall, they roll and they have these spikes. So those spikes kind of as compresses like springs and increases the amount of time that impact. So when they fall, there's an impact force from the ground, and as the spikes compresses, the impact time delta T increases, and what happens? Impulse F delta T. So the same force, if delta T increases, impulse increases. All right. It's the same force. If delta T decreases, impulse decreases. What do they do then? This helps them to cushion the impact of force. So the same force applied, but the time it takes changes. The same thing goes here. If you are playing a water balloon catch, if you catch them with a force quickly, and then you have a large force applied in short time. So if the force is large, you will burst the balloon easily. But if you catch them and move your hands backward, the idea of catching will be the same impulse, but you will be increasing the time for that same impulse. So you will be applying less force and the balloon will not burst. Try it. The same thing happens here actually. Impulse is the same. So if I increase the time, if I decrease the speed, the force here, so it will be less force applied to my body or hedgehog's body, and they will get less damage. Another question here, a light plastic card and a heavy steel card are both pushed with the same force for 1 second, starting from rest. After the force is removed, the momentum of the light plastic card is, so apply a force, same amount of time to both, okay? Delta T, delta T. what will happen? This is before picture for both, and before. After some time, each will have a change in momentum, right? So let's say they start from rest. Does it say they start from rest? Doesn't, but oh, from rest, yeah. So initially no speed, no momentum, and then they will be pushed amount of delta t. They will have a momentum change. And that momentum change is equal to F delta t. That's equal to delta p. The same here, because I'm applying the same force, same amount of time. So the momentum changes will be the same. Both starts with initial speed 0. Their final speed will not be the same because the masses are not the same. M1 delta V1 and M2 delta V2. So their final speed are not the same, but their momentums, final momentums will be the same. Why? Because they are applied to same impulse. So the answer is equal. And if we do more thinking, assume this card is M, this card is 2M, and I'm applying the same force, same amount of time. So the heavier card will have a less final speed, but not momentum. Momentums will be the same. Again, why? Because they are applied the same impulse. Impulse is equal to change in momentum. Both started initially with 0 momentum, will have same change in momentum. All right, the answer is equal. Same impulse, same change in momentum. Altogether, summary is, if we apply a force to an object, we apply an impulse, and that impulse is equal to average force we apply times the time it takes that we apply it. If we have a force versus time graph, area under is equal to impulse. Second idea here is impulse causes a change in momentum, so impulse is equal to delta p, change in momentum, or final momentum minus initial momentum. Keeping in mind, momentum is a vector. If you guys feel like it, you can also use this approach. Initial momentum plus the impulse is equal to final momentum, which comes from here, the same idea. There's just some algebra done. But again, they are all vectors. You have to know the direction to be able to solve this correctly. And here's the summary. I can also write the change in momentum as mass times change in velocity. Depends on the question. Whichever one looks easier to me, I will use it. Momentum is a vector. It has a direction, and generally to find a momentum, we say mass times the speed or velocity. Again, velocity is the speed with direction. But we have momentum as vector. We have to be careful about that again and again. If I have a system of objects and I'm calculating their total momentum, of course, I am going to add them as vectors. Add as vectors. This example here, for example, is showing 3 momentum vectors and 3 momentum vectors, and adding them head to tail. Remember, we take the first one, then take the other one, not changing direction or the magnitude, length. We can carry them anywhere we want, right? Property of vectors. And then from the beginning of the first vector to the end, combining those, direction towards the end one will be the total momentum vector. We generally use, if we have more than one forces or momentums, any type of vectors, we generally use component methods, but idea is direction matters. This page summarizes the approach for solving momentum problems. Here is the long version. Please read it, go ahead, but I shorten it here. They say, look at the situation, draw a visual picture. So we draw an ugly picture. In this case, in the case of momentum, we're going to draw a before picture and after picture. Before an impact happens, then impact happens, momentum changes after picture. And then we will use impact, impulse is equal to change in momentum. We'll list all the knowns and find unknowns. Here is an example. A rocket sled. So that's a sled with a mechanism that pushes it if it wants it to be pushed. So you are sledding, sitting here. Has total mass of 500 kilogram. Assume this is you and sled together, but they're talking about like a sled alone. I'm making it more like applicable to life. Is coasting at, that's your initial speed, 20 meters per second. So I know the mass, I know initial speed. Then turns on its rocket engines for 5 seconds with a thrust of 1,000 Newton. So this will be my before picture here. Before I was going with that. My mass with the sled is 500 kilogram and I have a speed of 20 meters per second. Then what happens? There is a stage. I applied a force to myself for turning on my rocket engine. I wanted to have some more fun, so I'm pushing myself to a higher speed, right? All right. So I fire my rocket and that applies a force on me. Let me use a different color here for the force. That will be the thrust force. I'll call it F, but that's the thrust force by the rocket, right? And that's 1,000 Newton. And I apply that force for an amount of time that is 5 seconds. What happens? So this kind of the medium part, and after picture will be here for me. What will happen? Then I remove the force, right? Then I remove the force. What will happen is pretty intuitive. I'll have a larger speed. My V final will be larger than V initial. I don't know it. And I'll be going at a larger speed. Now the force is removed between before and after I applied the force in here. That will cause a J impulse, F delta T, which will cause a change in momentum. And change in momentum is equal to M delta V. I put down all my nouns. I did some thinking. I'm thinking of the physics will be that. So I look at now what I'm asked to find, the final speed. So I'll go with this. J is equal to M delta V. What is J? Force times delta T is equal to mass times. I'm going to go with V final minus V initial here. Always feel free to start here. Put in the values. Mind in the direction of the vectors that you know. V initial is plus. And if we final, in this case, we know that it's going to be plus, but sometimes we will not know. Then we'll just put them in and the results will tell us if it's plus or minus. But in this case, it's obvious that it will be plus. As the time goes on, we'll have some collisions and so on. Then we may not know. I know my force 1,000 Newton. Not 100. Not 100. 1,000 Newton. Let me redo this here. Times the time, 5 seconds. Equals, I know all the mass of me and the sled. I turned it to that. It said sled, but I'm going to be on it. I don't know V final, but I know V initial. 20 meters per second. So all this is just one unknown. Easy algebra question, right? All right, so when we final from here, I'm going to leave it up to you folks to go through all algebra. I'll give you the answer. So do some work here for me, will you? V final should be, let me find it, should be 30 meters per second. All right, it's your duty to please do all the algebra here, not very hard, and find that number.